Yes.
Okay.
I was always busy with that.
So here we go. I would like you to help me verbalize it. Okay? So Eli, give me something that you guys discussed. What were you looking for with continuity?
The two limits from each side and the actual value at x all need to be the same.
All need to be the same. Anthony, do you think what he explained sounds accurate? Why? Okay, I like that. Okay, so Eli said right-hand limit, left-hand limit, function value all need to be the same. Anthony's saying, well, because when you look at it, it's just nice and smooth, right? There's no breaks. There's no holes in our graph, right? Are those like the big things that you were looking for when you had something that was not continuous? Holes or breaks? What do I mean by a break? Okay, like a jump where you have like two lines, but, right? Okay, so first of all, I mean, plain and simple, if we want to use simple terms, a continuous curve has no breaks or holes. Okay? That could be like you're explaining it to somebody in Algebra 1, right? Okay? We're going to talk about the formal definition, which is essentially what Eli described for us back there. Okay? When we talk about continuity, okay, there are three things that we are looking for. Okay? So, write definition of continuity, and you're going to give me and write 1, 2, 3. Number 1, f of c is defined. That means we have a function value somewhere. Okay? Don't worry about this stuff previewing it. Okay? Number 1, f of c is defined. Number 2, we probably have something to do with a limit, right? That's what you guys were looking at on your pictures. The limit as x approaches c needs to exist. I told you there's 3 stipulations. Think about what that third one's going to be. Whisper to your neighbor, what has to be the third stipulation for this all to work? We have a function value, we have a limit. What should be true about that? All right. Grace, what has to be true? They have to equal each other. That's what Eli explained to us at the very beginning. We have a limit, we have a function value, and they need to be the same. That way, we have a curve that's nice and smooth with no breaks or holes. Okay. Okay. I'm going to show you some counter examples for when this would not be true. Okay? Just sit back and enjoy. All right? Don't feel like you need to draw these. Okay? You've pretty much experienced these in your activity. Okay? Here. we have a hole, and that's going to jump out to you, right? We don't have a function value at all. If there's no function value at all, there's no way for it to be continuous. Okay? But basically, since you see that hole, you know it's not continuous there at C. Here, we have a function value, hooray, but the limit at C doesn't exist. And so this is not continuous. What's jumping out to you in this picture? It's broken, right? We have a jump. Okay? That's going to be kind of like a big red flag. Okay? In this one, we have a limit and we have a function value, but they're not the same. The coordinate is somewhere else than the hole. Okay, so this is not continuous. Essentially, if you can't take your pencil and draw the whole curve without lifting it, there's some sort of discontinuity. Okay. How do you feel about that?
Easy.
So here's some pictures that we're going to describe the continuity. Okay? Sine of x. Do you see anything? Do you see any breaks or holes or anything in this picture? Okay? Then we would say that it's continuous everywhere. Continuous everywhere. I want you to think of another type, another family of functions that would be continuous everywhere. Think about it. A family of functions that would be continuous everywhere. Turner, what do you think?
Cosine.
Well played. Okay. Maybe not a trig function. Okay, let's step out of the box a little bit. Caitlin, what do you think? A line, a linear function would be continuous everywhere. Let's build off of that. A parabola. What do we call a line and a parabola? What about that stair-step function? Stair-step function, that wouldn't be. Instead of parent functions, line, quadratic, cubic, quartic, what do we call those? Polynomials. Our polynomial family would always be continuous everywhere. Okay? All right. So, Aaron, let's talk about this parent function. Okay? Is it continuous? No. Could we say right here that it's continuous from 0 to 1? If I was looking at just that part of the graph and nothing else, is it continuous from 0 to 1? Yes. Why do I put a bracket on 0?
It includes 0.
It includes 0. What about 1?
It doesn't.
It doesn't. Okay. This semicircle. Okay. Would we say that it's continuous across all real numbers? No. But it does have some continuity. Right? Okay. Christiana, where would we be continuous on this semicircle? -2, 2. Okay. Good. What is something else that we might need to worry about making something discontinuous? We've talked about a hole and we've talked about a break. There's one other feature a graph could have that would cause it to be discontinuous. You said this. Can you explain what you mean by that? Like, can you give me an example?
I was thinking like if you have to go like an asymptote or something like that.
Oh, like an asymptote. Yes. Would an asymptote break up a graph?
Yes.
No matter what, right? A vertical one? Okay, an asymptote would be a discontinuity we'd have to be careful with. Okay? We're doing great. We are doing great. Go ahead and write down this example. We're going to do a little bit of work here. Well, you're whining back
No.
Okay. We want to force this function to be continuous. We know the function value needs to exist, the limit needs to exist, and they need to be one and the same. Okay. Where are we worried about? Are we worried about x is 0? No, we're worried about x is 2 because that's the break in the domain. So first we need f of 2 to exist. Okay? Where are we going to plug 2 into? The top or the bottom piece? The top piece because we include 2. So we have a times 2 squared, which is 4a. Okay. Secondly, we need the limit to exist. So the limit, okay, since we have a piecewise function, we must consider the limit from the left, and we must consider the limit from the right. So the limit from the left would be that ax squared, right? The limit from the right, x is greater than 2 at x plus a. So x plus a. Now if we want the limit to exist, what needs to be true about the right and the left-hand limit that we just found? They gotta be the same. What's A? Yeah.
Yes. Is it 2/3? Maybe it flips it. Oh yeah, I did flip it. Basically, there's some numbers.
It's okay, we got the calculus part.
Yeah.
Okay, so A is 2/3. Okay, so let's check it here. Our function value would be 8/3. Our limit from the left would be 8/3. Our limit from the right would be 8/3. So our function value and our limit are the same. We have forced this piecewise function to be continuous. Okay. Essentially what's happening, and I don't know exactly what it looks like, so don't quote me on this here. Okay. But it's looking something like that. Parabola with a line and they connect. Are we okay over here? Yeah. Okay. All right, so very quickly, we're going to talk about two different types of discontinuity. When I say discontinuity, Dylan, what would that mean? Okay, I can break it perfectly. Break is fine. Or okay, we We have a break, we have a hole, we have an asymptote. Now, there are certain kinds of discontinuities that we can fix, and there are certain kinds of discontinuities that we can't fix. So we call them removable and non-removable. I'll let you go ahead and write them down, and then I'll explain to you what I mean by that. Okay. Basically, a removable discontinuity would be like a hole that we could fill in with a coordinate. Okay? If we had a function that looked like this, we could add to that function by saying, okay, well maybe x can't equal 1, but when x equals 1, we could fill in that hole. Okay? If you have just a hole on a curve, we could fill that in with a coordinate. We would consider that removable. We could fix it. A non-removable discontinuity, it's always going to be discontinuous no matter what. And vertical asymptote, we can't get rid of it. It's there. Okay? A vertical asymptote would be an example of a non-removable discontinuity. Okay? So let's look at an example of each. Okay? Here I have x squared minus 1 over x minus 1. I would suggest writing that down so you can write down the work that I'm about to do so we can see, you know, how you would answer this question on your quiz come Wednesday next week. We have a 3-day weekend, isn't that a thing?
Yes.
We all need to recover, right? Yeah, Monday's Labor Day.
I realized that for like a second.
And then we have a 4-day weekend next weekend. Because we have school on Friday. The day before homecoming.
We have a 4-day week and then a 4-day week?
Yeah, I think so.
Okay. It is just rough for you guys.
I know.
Okay, so let's talk about algebraically how we would know that this is a removable discontinuity. Okay? What can we do to the numerator?
Factor.
Thank you for your enthusiasm, Eli. Okay. Since our x minus 1s cancel out, that tells us that we have a hole at x equals 1. Okay. So we have removable discontinuity. What?
Nothing.
Are you wondering what to do with the x plus 1?
Yeah.
Okay, well, if I were just to ask you where and what kind of discontinuity we have, you would do the algebra to determine we have a hole there and tell me it's removable, and then you would be done.
Oh.
Yes.
Do you need the book? It's at my house still. Bring it tomorrow. What? What are you?
Promise?
Oh, I promise. I'm responsible. I'll get it tomorrow.
Okay, does that answer your question?
Yep.
Okay. If I were asked you to graph it, then you would graph x plus 1, the line with a hole at 1, but that's probably not what I'm worried about. Probably worried about the discontinuity. Okay? If you had an equation like this, f of x equals 1 over x.
Wait, with the last one, how do you just like put it back in?
So what we could do is we could like make this a piecewise function. Like x can't equal 1, but then y is 2 when x equals 1. Have you seen like piecewise functions like that? Yeah, we could write it to where we could just fill in that hole. That makes sense?
Yeah.
I'm not going to make you do that, but we could if we wanted to. Okay? F of x equals 1 over x would be an example of a function that has non-removable discontinuity because we have an asymptote, and I'll draw it bright red for you here. Okay? The denominator equals 0 at 0, and there's no way algebraically to get rid of that x in the denominator, so it is an asymptote. There's nothing we can do. We have non-removable discontinuity. So I really think that we have talked enough about things to where you're going to be able to do every problem that I assigned this evening. What I do want to do, because we have 5 minutes, and you're not going to start your homework in 5 minutes, so I will at least want to talk about 3 to 4 examples, and then we can talk about the rest tomorrow if we need. Go ahead and write down these 2. Caleb, which one would you like to start with, number 1 or number 2?
Number 2.
Number 2, is there a reason that you're drawn to number 2?
Just kind of scares me.
Tangent kind of scares you. Thank you for being honest. Okay. What type of equation do we have in 2x cubed minus x? A polynomial. And what did we decide polynomials would always be?
Continuous.
They're always continuous. So we are continuous everywhere. That's also a nice way to start out, right? First example is just continuous. Now, number 1, tangent. Kind of gave us a little bit of insecurity there. Okay? When we're talking about discontinuities, really we're worried about fractions, would you agree? Because whatever makes the denominator 0 in a fraction is either going to create a whole or an asymptote. So instead of writing tangent of x, what maybe could we write here? Okay. So you can either think about what the graph of tangent looks like. Some of you know where those vertical asymptotes are. Or if you're unsure, we can write it as a fraction, and we know wherever that denominator is 0, we're going to have asymptotes. So first of all, we have asymptotes. We need to identify if we have removable or non-removable discontinuity. Removable or non-removable. Chris, are they going to be which one? Okay, Chris says non-removable. Nick, is he right? Nick only thinks so. Why do you think so?
Because we have asymptotes.
Okay, non-removable. Okay, where does the cosine equal 0 at? all of the times we're at like north and south on the unit circle, right? Okay. So here's how we could describe that. Are you ready? How far apart are pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over how far apart? Okay. So we could write this as pi over 2 plus pi times n. And then that would describe all of the places. And just because I think it will only take a minute and a half, we're going to do our one more example. This one right here. 5x over x squared minus x. Yeah?
Were you saying that we can make it a continuous? Is this still a discontinuity?
Yeah. Yep. So in our denominator, do you agree? We have x times x minus 1?
Yes.
Yes. So that's happening, right? So at x equals 0, we have removable discontinuity because we have a hole. But at x equals 1, we have non-removable discontinuity because we have an asymptote. If we cross out factors, we have a hole. It's removable. If our denominator remains 0 after we simplify, we have non-removable. It's an asymptote. Okay, do what you can on your homework, and we will continue our conversation tomorrow. And you'll get your quizzes back, and we'll be able to talk more in depth about your quizzes, okay? Check your grade if you want to, though.
All right, right now.
Something go under here? Here? Okay. Nick, you had put that on here?
Yeah. And like most of them have
Okay.
like straight.
We have math
Yes,
class,
so like
right?
this, so, yeah.
And you're gonna be there?
Let's go. What's this?
Okay.
Why are you pointing at me?
Different practice days.
Okay.
And I would like 20 plus minutes. Yeah,
Okay. Thank you very much. How long is my time? But like what? Like the August.